Hello everyone, my name is Yang Hu and I came from Dr. Jeremy Levy's group in University of Pittsburgh. Today I want to talk about development of single-electron and electron-pair sources in lanthanum, aluminate, and strontium titanium nanostructures. Single-electron and electron-pair sources are useful because it is useful for initialization of quantum bits. And also it is an alternating current standard for possible applications in metrology. People has realized the single electron transport in several ways, so here's one example where they are using double quantum dot system. So here there's a left dot and a right dot, and they have a current source, current drain, and there are two gates to tune each dot. So when you change the voltage on a side gate, you can change the distribution of electron numbers on the left and right dot, which is showing as a left number and a right number here. And if you find a specific coordinate of the voltage and change the voltage periodically, you can realize the single electron transport in one period, so that the current you measured will be proportional to the frequency of the voltage changing, which is showing here. So this is one example. Another example where people realize single electron transport is they use a surface acoustic wave. Because surface acoustic wave can create local potential minima, and if you use such minima to trap one single electron, and you can use this minimum also to drag this single electron, so that you can move the single electron from one place to another place to realize single electron transport. So my project is realize the single electron or electron pair transport in lanthanum, aluminate, and strontium titanium heater structure, which can be called as LaSTO. So we use this material because LaSTO has many interesting properties. For example, the interface can exhibit high mobility to the electron gas, and the interface can show an insulator to metal transition when the top LaO is about 4 unit cell thick. The interface also shows tunable superconductivity, tunable magnetism, and tunable spin-orbit coupling. So here's how we create devices in the interface. First, we get the material, and then we deposit electrodes to contact with the interface, and then we put a conductive AFM tip on the surface. If you apply a positive voltage to the tip, you can deposit some protons to the surface, which will attract electrons from the STO substrate to the interface, so that you can create a conducting region. And if you drag the tip, you can write a conducting wire in the interface, whose minimum feature can be as small as 2 nanometer. And when you apply a bias AFM tip with a negative voltage, you can also create a barrier to the interface, so that you can cut such wire. And during this process, no physical modification was made, and this process can be repeated for many times. So this is a picture showing such process. So you can see that the green region are the conducting region written at the interface using a conductive AFM tip biased with a positive voltage. And wherever you want to create a barrier, you can bias a AFM tip with a negative voltage, so that you can draw many kind of devices on this canvas. So using this technique, our lab has fabricated many interesting devices. For example, this is a single electron transistor. We have also written electron and Cooper pair waveguide, and we realized ballistic transport in micrometer scale in the interface. Also, we have observed electron pairing without superconductivity. And here's this is my device for realizing the single electron and electron pair transport in the interface. So this is a top view of the lanthanum, aluminate, and strontium titanate heater structure. And the yellow part are the electrodes, and the green part are the region written with a positively biased AFM tip. So we have a left dot, right dot, and in the middle there's a nanowire. And I will be applying a AC signal to the current source, and will measure the current using a lock-in from the current drain. And there are two side gates to tune the energy level of the left dot and the right dot. So this is a close look at this central region for the left dot, middle nanowire, and the right dot. And this is how I write these devices. So first I use the positively biased AFM tip to write a conducting wire in the interface, and then I hold the tip at the position where I want to create a quantum dot. So I apply the voltage pulses whose shape is like this. So there's a negative voltage pulse to create a barrier, and the following positive voltage pulse will create a quantum dot. Using the same method, I will create a second one and connect this to the current source, current drain, and the left side gate and the right side gate. So I cool this device to a 2K, and when I change the voltage on the left side gate and the right side gate, I have observed some interesting signal, which is like this, where you can see that I can only see some finite signal along this line when changing the side gate voltage. And if you take a line cut, the signal looks like this, where you can regard a signal as a combination of wide but low peak combined with a thin but sharp peak. And this is a signal measured at zero magnetic field. So later I change the magnetic field and the signal will change like this. So this is a signal at 2.2 Tesla. This is at 4 Tesla, and this is at 2.8 Tesla. And you can see that at when the magnetic field is 2.2 Tesla, this peak is not splitting. But when the magnetic field goes larger, the peak starts to split. And we think that when there's a kind of a critical magnetic field, so that below this critical magnetic field, the peak is not splitting, and the electrons are paired. And the signal we measure comes from the transport from the electron pair. And when the magnetic field goes larger than this critical value, the electron pair get separated, and you can see the peak splitting. So this is how such signal change with magnetic field, and you can clearly see that the peak only splits above some critical magnetic field. Actually, we have already seen such signal in some other devices in our lab. So this is a paper showing the signal, and this is the device they are using was so the device contains one nanowire quantum dot in the middle, and they are using circuit to tune this dot. And when I change the circuit voltage, you can also see the current signal change like this, and you can also see such peak only split above some critical magnetic field. So actually the splitting versus magnetic field graph is like this, where you can see that there's some critical magnetic field, and the value for this graph is about 2.6 Tesla. And temperature for this measurement is about 2K. Then I repeated this measurement at some other temperatures, and I can always see the similar phenomenon up to a point about 3.2 Kelvin. So the mechanism we think for now is like this, where you have the left is like the electron reservoir for the current source, and the right is electron reservoir for the current drain, and here are the discrete energy level for the left quantum dot, right quantum dot, and in the middle the nanowire provides some tunneling channels, and when the magnetic field is small, the electrons are paired, and when the energy level of left and right quantum dot are within this range, this channel, the electron pair can get through, so that you can get this peak 1, which is wide but low peak. And when you change the side gate voltage so that the energy level of the left and right quantum dot are aligned with each other, the electron pair will tunnel with a larger probability, so that you can get this peak 2, which is a thin but sharper peak, thin but higher peak. And when you further increase the magnetic field, this electron pair will get broken, and they will tunnel through separately, so that you can different spin specified electron will correspond to the left and right peak. So that you can see that if we control the magnetic field below this critical value, we can send the electron pair, and if we increase the magnetic field above this value, we can send the spin specified electrons, so that this device can serve as either electron pair source or spin specified single electron source, or say kind of a spin filter. So currently we are making efforts to lower the time constant when apply voltage pulses, so that we can get a faster response. And we are also trying to avoid circuit leakage current, and updated software used for writing the quantum dots, so that we can improve the quality of the quantum dot written. So to summarize, LaAlO3 system is potential candidate for single electron and electron pair sources, and this project can also be combined with another project in our group, which is relevant to the using a surface acoustic wave, which is in this session. So here are the other talks presented by our group. You can feel free to listen to these talks. That's all. Thank you.